Okay, so we're going to talk about motional electromotive force and Faraday's law, and to do that we're going to illustrate the world's worst electrical generator. So what we need to do first is we're going to create a magnetic field going into the page. Okay, so that is our magnetic field. Within our magnetic field, we are going to create a system where we have two conducting rails. Okay, a resistor in between them. Okay, and another conducting rail on the other side. Okay, so it looks like this, where these are just rails, and we're going to slide something along these rails here in a sec. So, rails with a resistor in between them. All right, they are a distance L apart. And on these rails, we have a copper conducting slide. Okay, and this slide is free to move back and forth along the rails. Okay, and we're going to give it an initial velocity. Let's zoom in a little bit, you guys can see. Okay. So, if we move this rail, okay, what is happening to the amount of field lines that are in our loop? Okay, so if we slide this way, okay, we start increasing the amount of field lines in the loop, right? Okay. And if we do that, okay, then what happens in our loop right here? Because you can here's our loop. Our loop goes is going like that, right? That wherever this rail is, that's the other side of the loop, yeah? Okay, so, Nick? Okay. All right, another thing I want to do with this is I want to establish this is 0. That's the x direction. Okay, just for right now. Okay. In our rail right here, kind of hard to contrast, we have these charges. They're theoretical positive charges. We know they're not real positive charges, but they're in there, right? Well, theoretical positive charge. Okay, so if we move our rail in this direction, okay, where's the positive charge going to want to go? Aha. Remember, we put our fingers, okay, point our fingers in the direction of the velocity. Okay, curl our fingers in the direction of the field. And look at the lovely little mark I've got on my hand. Okay, and this is what happens, by the way, when your dentist isn't happy with you in the chair. No, I'm kidding. So the force on all these particles is actually going to be that is the force acting on the particle. This force is governed by the equation force equals, ooh, you guys remember this one?
IL cross B.
Okay, or it could be
Q.
Phil Crosby. What's the other one?
QV. QVB sine.
Okay, or just QV cross B, right? QVB sine theta or QV cross B. Right? This is the force on a moving particle. Well, we can also just look at the velocity that this thing is moving, because this is dragging the particle with it, right? The particle's not leaving the rail, it's dragging the particle through with this velocity. The magnetic field is into the page, which means this particle is going to move in that direction. Oh, wait a second. It's causing a charged particle to move in a conductor. What must that be? What's that? Oh, adrift? What? Well, yes, the particle's moving in a current, but what causes a current?
Voltage.
It is a voltage. And this right here creates, okay, this creates an electromotive force. Okay, because the forces on a charged particle in a conductor, okay, means voltage. So, we have our force equals QVB. We also have our force equal to Phil cross B, right? Okay, and here's our L, because this would be the length, right? Here's our L, L cross B. Okay, now, let's come back over here. What if I take this Q and we divide both sides? What is force per unit charge? That's our field, right? Force per unit charge creates an electric field. Okay, so look what we've done here. All of a sudden we have an electric field equals V cross B. Or we can just, and since they're all perpendicular to each other, we don't have anything at funky angles. Our electric field equals our velocity times our magnetic field. Okay, this look what this tells us. If this stays the same, we have this velocity, this thing moving through. If we're moving this through our magnetic field, okay, it's creating an electric field. Yeah? Or if we go the other way, if we change our electric field, that stays the same velocity, what's going to happen to this? Okay, we have a changing magnetic field. Okay, this is a bit oversimplified version of Faraday's law, but this is one of the most profound ideas in all of electricity and magnetism. That our electric field and our magnetic field are inextricably related to each other. And it took a long time to get these two ideas. That previously in physics, 150 years ago, in physics you would have electricity and you would have magnetism, and they would not relate to each other. And only through Maxwell's equations did we finally get, we'll get to those in another lecture, did we finally get a synthesis of all of electricity and magnetism. Okay, now, we have a voltage we have a voltage here that if we have this magnetic field that's acting across this distance, right? We have the magnetic field, the electric field is going in that direction, right? Yeah. And that's acting from this distance to there, which is distance L, right? So the voltage drop is equal to EL. Yeah? That make sense? Okay. our electric field is D, and that's our force per unit charge. Yeah? Okay. But our potential difference, if we have an electric field, our potential difference is the difference. It's the difference. It's the difference in potential between 2 points in an electric field. So if the 2 points are here and here, then that distance is L. So our total voltage is electric field times that distance L. Yeah. Okay. But we just figured out what E was, right? E was this over here. So we're going to plug that in there, and we're going to get our voltage equaling. Okay, and the convention for writing this is B, we're changing voltage, BLV. Okay, and this is our motional EMF. That's delta V. Our change in our potential equals BLV. Okay, so it's the field. All right, now we are getting into some, for hundreds of years, a little bit of history here, physics is all based on stuff that made sense to us. And what Newton did with his mechanics was come up with a way to actually measure the things that already made sense to us, but we could just measure it in a better way. Electricity and magnetism, we don't get to see these effects all the time. And they don't always make straight up sense to us. So this does require some study, and it requires going over on your own part and over and over and over again until it really becomes second nature to you guys. And it requires some pretty heavy thought, because this is not necessarily common sense. Okay, which is what Newton did. Newton just measured common sense. Okay, this is not common sense. Okay, this is much more abstract than that. So some of these things, for those of you that have to know why for everything, you have tend to have a more difficult time understanding what's going on. Sometimes you just have to accept it and move on. Okay, and let it all come together, guys. This stuff didn't come together for me until very recently, and I'm still piecing it together as we're going through this. So it takes a while for it to get in there, and we don't have a while, do we? Okay, so that means it's more reps. We need the reps. We need going over it and making sure you guys are understanding this. So, okay. However, we can take this, and we know according to Ohm's law, which is V equals IR. Okay, that our current equals our voltage over our resistance. So we can take this, and we can find the current in this loop is equal to BLV over our resistor right here, which I didn't label, but that would be R. Okay, so here's our resistor. The current through this loop is going to be whatever our voltage is divided by that resistance is going to give us our current through that loop. Okay. So let's go back for a sec. Let's think about this. If we have a charge that's moving in this direction, isn't that also making a field? Okay, so now all of a sudden our field is in that direction, right? Okay, and so if we're moving in this direction and we have our current curling around, right? Okay, the way I say it, if our current is, well, which direction is the current, by the way, going to go? Going to go clockwise or counterclockwise? Okay, this is going to go counterclockwise, right? It's going to curl. It's going to curl like that. But what does this mean then? Because if that's our current, what does the thumb up mean? Aha! It's coming out of the page, not into the page. Okay, so whoa, wait a second here. We have a standing magnetic field that's going into the page. We move this slider to the right to increase the amount of magnetic field going through the loop. And what happens to the current? We get this counterclockwise current, but what happens? The current then generates its own magnetic field, right? Which is in the opposite direction. Okay? No, they don't. Not quite. Okay. We're going to get into, we're going to talk about, well, we'll get to that here in a minute. But this is, however, this is how we make electricity. This is how electricity is made. Now, this is the world's worst generator. This is not how we really do it. Okay, we don't have somebody standing there with a copper slide going like this. Okay, and creating electricity. Okay, think about what would happen. What if, after time, we move the slider out here, right? Okay, and we do this to it, and we move the slider back. Okay, we have a velocity in the other direction, right? That creates a current in the other direction, right? So if we have this thing going back and forth, we create all of a sudden an alternating current. Oh, that's why we have AC rather than DC. It's because this is how we generate our electricity, is in this alternating direction. We have things looping around and spinning. Okay, so that makes this go back and forth through our magnetic field. Okay, physicists make this. We go out and we tell engineers it's possible to do it. Go for it. And the engineers take it and they make something beautiful and efficient and useful. Physicists don't do that. We just tell them, we tell engineers what the rules are, and they go ahead and manipulate the rules and figure out how to do it. Okay, so that's, you know, there's a physicist, mathematicians, physicists, and engineers joke. You guys heard this one? Yes, you have heard it? Yes, the trash can on fire. I've already told it. Okay. Okay, well, there's a trash can on fire, and you have a physicist, a mathematician, a physicist, an engineer looking at it. And the mathematician well, no. The engineer goes and he runs off and he goes to get a pail of water. The physicist stands there and looks at it and says, I think we can put the fire out with some water. And the mathematician looks at the problem and says, a solution is possible. Okay, so. Okay. Now, what I want you guys to think about, though, is that there are other applications to this aside from just generating electricity. Or there are other ways that can be used in order to generate electricity. Hybrid cars use this kind of idea. Due to Newton's third law, if there's a force acting on these particles, okay, there has to be an equal and opposite force acting the other direction, right? Okay, well, that's what you're getting when you're moving. You can't just slide this rail back and forth. Okay, the greater the velocity, the greater the force, right? So it's hard to move this slide through our magnetic field. Well, what if you already have something moving fast and then you engage a magnetic field? What do you think would happen to our current here? If we engage a magnetic field, okay, all of a sudden we create a current that has its own magnetic field, and it makes this slow down. Right? This has a velocity. If we cause this to decelerate, this velocity, by engaging a magnetic field, all of a sudden we're creating a current, right? Instead of, if we have this constant velocity, okay, let's say it's spinning, okay, and we engage a magnetic field, okay, so now this thing isn't spinning, it's going to slow down, okay, but in the process of it slowing down, it creates a motional EMF. Okay, this is how hybrid engines this is how regenerative braking and hybrid engines gather their energy. Okay, because it requires, they engage the magnetic field, and the magnetic field is the force that slows down the spinning of the tire, and the spinning of the tire sends electricity back to the hybrid battery. Okay, and so instead of you guys are driving down the road and you get up to speed, and then it's like, so you're like driving down Shaw, and then every mother flipping stoplight turns red on you. You don't have to get angry anymore because every time that happens, you're really saving gas. Okay, and so the longer the trip, the more stopping and start. The weird thing is, the more stopping and starting you do in a hybrid vehicle, the better your gas mileage gets. Yeah, you get better city MPG than you do on the highway. Why on the highway? Because you're not stopping. You're not regenerating your brakes. You're not taking this energy that you use to get up to speed and then converting it back into electricity when you slow down. Okay, your energy drain when you're at speed is coming from aerodynamic drag, okay, and a little bit of friction with the road, and that's a constant drain on your energy supply. Stop and go traffic's a breeze for a Prius. Okay, or other electric vehicles. Other electric vehicles also use the same thing. Okay, so that's one of the genius of using hybrid vehicles is this regenerative braking. Okay, I want you guys to look back up here at this. Shh, come back. Look back up here at this. What is V? This is our velocity, right? Is there another way that we can relate velocity? Okay, well, it's our change in distance over time, right? Okay, well, if we have x right here, then what is our way of relating position and velocity? Velocity equals dx dt. Okay, so keep this in mind because I'm taking it off the screen. What's our formula for a magnetic flux? It's the magnetic field times what? Times the area. Okay, what is our area right here?
The dx, L x L.
For this rectangle, it's x, right?
LX.
So this, whatever x value this is, times L, right? Okay, so our area is equal to B times Lx, right? Shh. Guys, our flux equals B times L times X. Yeah? Okay, but if we were to take the derivative of this, we get that, yeah? But what's this? This is our voltage. Right? d phi dt of our magnetic field is actually a voltage. So, well, how do we get this? Well, this dx dt is BLV, right? Right, so d phi dt is our voltage. The change in the magnetic flux is equal to our voltage. Okay, we will call, well, actually it's equal to the change in voltage. Okay, and we will call this is how we get electric generators. This idea, we're going to call this EMF, by the way, that our electromotive force is equal to negative d phi dt, and this This is Faraday's law.
Wait, so it's negative?
Ah, and there's the question. Negative? Where did the negative come from? All right. Here's where the negative comes from. Okay. As we slide this way, we are increasing our flux per unit time. The number of field lines going through our loop is increasing per unit time. Yeah? Okay. If that's increasing, that's still creating a force. We know that the current is in this direction, right? Okay, current is counterclockwise. Okay, but that creates a magnetic field that's in the opposite direction. That's where the negative comes from. That the electromotive force comes from, will result essentially in the negative magnetic flux that was used to create it. That's Faraday's law. This is the electricity magnetism version of Le Chatelier's principle. Oh, what? You chemistry people. Okay, if you remember your chemistry, if it's just sitting there, or let's try this. I want you to think about this for a sec. If I take this slider and I go like this, I take it and throw it. What is this slider going to do? It'll go this way and then do what? And then come back. Will it stop here? No. It'll oscillate. Okay. It'll go back. So, if this is where it is, where there is no force on it, okay, where the net force is 0 on this, what do we call this position? Yeah. Say it. Oh, I thought you said it. What do we call a place in an oscillating system where the net force is 0? It's equilibrium. This is an equilibrium position. Oh, wait a second. Equilibrium, what is Le Chatelier's principle related to? Equilibrium. Whoa. Okay. So I really want you to think of Faraday's law as okay. Le Chatelier's principle is if you tweak one side, okay, the other side's going to do something to fix what you tweaked.
It's for equilibrium.
Okay, it's for equilibrium. If you tweak one side of the equation, okay, the other side is going to change to try and undo what you tweaked. If you give this a shove, if you twang this, okay, hold on, not kidding. Okay, what if you go bing on an electric guitar? What are you doing? You're moving a string over a magnetic field, and you're creating a frequency which creates a current which runs through your electric guitar to your amp and gets transformed into sound, and that's how the magnetic pickups work on electric guitar. Okay, so because of Michael Faraday, we have Jimi Hendrix. Because of Michael Faraday, we have Eddie Van Halen. Okay. That's what those are. Those are the pickups that your vibrate. Okay. So, that's Faraday's law. Okay, aside from just electricity generating, that's another version. It's another real life example of how this works. But what do I want you to remember about Faraday's law?
Le Chatelier's principle.
Okay. It's nature. Faraday's law is nature's way of restoring something to equilibrium. It's trying to return something that you tweaked back to its equilibrium state. All right? And it does that with the voltage being equal to the negative change in the flux over time. Okay. That's it for Faraday.